Welcome to an introduction in the IR Absorption Table. This has to do with some of the numbers that you will see on what is called an IR spectrum. So let's get you back up to speed so we're sure you understand. IR stands for infrared, and by that we mean the certain kind of wavelengths that we can apply to a sample. And now the sample size is going to be small. It will be drops, for example, very small. And what happens is we measure how much of the wavelength is absorbed by that sample. And when we do that, we can actually determine what kind of functional groups, what type of bonds can be identified in a substance. So the general idea of IR absorption or infrared spectroscopy is to find functional groups right here. So just remember that. So this is a characteristic IR table. And there are several types of these on the internet, and it's just like periodic tables. There are many different versions here. But let me walk you around the one that we're going to use here. We decided to use reference letters in our absorption table. That way, when we're doing our work, it's easier to call something by A, B, and C rather than this span of numbers. Okay, so you'll see the red reference letter notation here obviously goes with those labels there. Now, the bond type and the functional group, they kind of go hand in hand. I'll tell you about that in a moment. But here you see the letter S and B. And we will see that on the infrared spectrum that S stands for strong, B stands for broad, and at the bottom of the table you'll see other references, for example, medium or weak. Okay, so that's just an indication of the general shape of the curve or peaks that you might see on the spectrum. Okay, so let's take a look at this first one here. It says this frequency, and it says centimeters inverted or inverse centimeters. Well, instead of using hertz, for example, it actually turns out to be very convenient to use inverse centimeters. And what that means is how many waves you get per centimeter. It's really just a different way than you might usually use in high school physics or high school chemistry. So in this method, inverse centimeters means that you can fit 3,500 infrared wavelengths in 1 centimeter. That just makes this scale convenient in size, so we can use these numbers here. So we're going to see in a moment what it looks like when you have a peak. Now it actually is a downward pointing peak, but there's going to be something in this range of 3,500 to 3,200. It'll be strong and broad, which means it'll be a deep signal and it'll be very wide. Okay, and there's a couple things going on here. In the molecule, you'll see that there's something called an OH stretch, and this H is actually stretching back and forth with this oxygen. And we've seen before that chemists would prefer that you think of these as springs, like a slinky, rather than a line or a stick. Okay, but if you get a peak in this region, then it says you have an alcohol in your substance. Now, phenol is an alcohol. It's an alcohol that has a six-sided benzene ring attached. So amines are very similar to hydroxyl groups or alcohol groups here, right? N and O are right next to each other on the periodic table. And this is also something you would see a little bit different here. You've seen this, primary, secondary, right? Because it has 1 carbon attached to it or 2 carbons attached to it. And then also the amide, that's the functional group that has the nitrogen and carbonyl group. Okay, and finally, just another example here of an OH stretch. This would just be the alcohol. Now notice something, by the way. The alcohol is a stretch between these two numbers, okay? But you also have that OH stretch up here in a carboxylic acid. Well, I'm sorry, you have this OH stretch here in a carboxylic acid, but you have this broad stretch here for alcohol, okay? So there must be something different about the OH group when it is on the carboxylic acid. So we're going to look at some of these details later. So again, this is the entire table, and we won't use all of these. There are some that we just don't see very often, but a lot of these are very important, and so they will keep coming up again and again. Some of the ones that we won't see very often probably are this triple bond stretch for alkynes, and some of these primary amines. We don't really have too many amine examples, at least in high school version of organic chem. You'll certainly see them in college chem. We don't see these halide groups here like the chlorine and the bromine. You'll definitely see the CH bend. In another example, you'll see this one a lot, okay, between 1000 and 1320. And two of the most common ones would be the C double bond O, called the carbonyl, although some people call it the carbonyl group. I've seen it called carbonyl. And then up here, alcohols and carboxylic acid are also very common. Let's first look at this example of hexane, and this is an IR spectrum, so that's what we call it. It's not a graph. I mean, it looks like a graph, and it's better if you call it a spectrum. Okay, but down here we have what is called the wave number. Now, on our absorption table, they called it the frequency. It's the same thing. Okay, it's the same thing here. And so we have this list of numbers between 4,000 all the way down to something like 500. You have to be a little careful here. These graduations here, for example, here is between 3,000 and 4,000. Each of these is 1,000 or 100. Yeah, it's 100. Okay, but over here you see between 2,000 and 1,000 you only have 5 gaps. So that's to keep this relatively easier to see, so we don't have to spread the whole graph out. Okay, so what are we doing here? Okay, we would first look at this peak. This is obviously very noticeable. Okay, this is called a peak. I know it points down. Sometimes you have absorbance over here. I've called it absorbance, and if you did, you would put 100 down here and 0 up here, but we can go with transmittance. You're going to see this peak. Okay, and it's important to see that the 3,000 is right there. Just to the right of the 3,000 is this peak here. So what does that tell us here? Well, this is our structure. This is the hexane molecule. Not a lot going on. There's no oxygen. There's no double bonds. There's not much going on at all. Okay? But we have two things of interest that are going to show up on the absorption table. First, this is a methyl group that's hanging on the end. And what happens is when you have infrared spectroscopy, this thing can sway back and forth. Okay, so it has a tendency to sway back and forth. And we're going to see that that is indicated right here and here. There's actually two absorptions for that. Okay, so these two peaks tell us that we have that guy right there. Okay, most of the rest of the molecule, right, has these CH bonds. Okay, that is so common in organic chemistry that that's almost not helpful. But alkanes are single bonded carbon-hydrogen bonds. So this is called an alkyl group or an alkyl bond. And so all of these, 1, 2, 3, 4, all of those, and the CHs, they also have the CH bond. They can be found over here in this 3,000 range. Now we're going to look at the absorption table, and we're going to see just exactly what that means. All right, welcome back to the absorption table. And the last peak that we just talked about is just to the right of 3,000. Now remember, our numbers go the other way, so that area right there, that one that we talked about hanging down, tells us we have alkanes or alkyl groups or single bonded carbon hydrogens. But that is, like I said, that's so common in organic chemistry that it's not very helpful to us. You're just saying that you have carbon hydrogen bonds. Well, that's not very specific enough. But down here you have this interesting thing. It actually has two, and we don't see that much on absorption tables, but there's two peaks at 1450 and 1375. Now, they don't have to be exactly at those positions. They can be close. Other things might factor in, but generally in these areas, the CH bend, and that could be this methyl group, like it says CH, but really you're going to see it more often as a methyl group, okay, so that there's this bending that's going on, and it must absorb at these two frequencies. That's pretty much all that says. But let's take a look at two different versions of a spectrum now, because if you'll notice here, this is hexane, single bonded, and then this guy is hexene, right? So that's the only difference between these two molecules, is that C double bond right there on the end, okay? So what do we notice? Well, this peak here that we had in the original hexane, right, is a little bit larger here, and we're not going to get into the reasons why, but now we have this other peak right here that is now to the other side of the 3000. And so we can look that up and see if that tells us anything specific. We are going to find out, actually, that tells us about that double bond there. Okay? Now, if we go up here, we can also see that's pretty much the same as the one that we had before. And this one is also in there. Okay? It just looks like this got a little bit larger in size. Okay? But now look at this. We have the presence of two more peaks. It just looks like we have more stuff going on here with hexene. Well, that brings us to this section here called the fingerprint region. Now I know there's something that showed up here, but this is called the fingerprint region. And what happens is this entire molecule, by virtue of its shape and size, for example, it does also absorb. And so that's really what we're seeing here, because the only difference we have between the two molecules is a double bond here. But one of the other things that we see is that the entire molecule has a characteristic absorption of these waves. Okay, so sometimes these waves tell us a lot, these peaks tell us a lot, but sometimes they don't tell us much at all. Okay, so we're just learning how to read these, but let's go back and make sure we find out what that stands for. That little peak that we saw then was a CH stretch, right? So we saw it to the left of 3000, which in this case puts 3000. Now it says weak to strong, so it depends on the molecule, okay? But I want to point something out here, that we do have an alkene, that's a C double bond, but also remember that alkenes, benzene rings, or six-sided cyclic structures, right? If they have alternating double bonds, and so we call those aromatics. So you have to pull back some of that knowledge that you have on naming of chemicals. This is a similar approach to what we had with hexene and hexane, right? That we take two structures that are fairly similar. Let's just look at the difference in their spectra. Okay. Now this is cyclohexene. It's a six-sided structure, as is the benzene, but we only have one double bonded here, and in this case we have two more, and they're alternating. All right. So what are the differences? Well, there's a couple noticeable, but nothing really big. This one has that alkene, right, the C double bond that we talked about, and that also appears here. The difference is now that this is an aromatic only because you have alternating double bonds. This is not an aromatic because it only has a single double bond, right? But you also see this. Now if you remember, that is a CH stretch, right? That is that's just below 3000, called a CH or alkyl stretch. Lots of CH bonds there. Look at this. There are no CH bonds here, right? Very few, very few, right? And so that's why you get a real skinny version of that, because you only have 1, 2, 3, 4, 5, 6. Here, though, you have more, because you have the CH2s. And so that's what shows up here, okay? Some of these little ones, not so significant. That doesn't really tell us much, okay? and perhaps this one does, and that looks like it's around the 1500, and that would be the alkenes. Just another example of how to compare two spectra for two different substances. Now this is a different example, and it helps reinforce the idea that you should make sure that you're paying attention. This is an OL, so this is an alcohol, OH, but this is octanol, and there's an AL, and so it's an aldehyde. So let's first look at the ethanol, and then we'll compare it to the octanol. Ethanol has this characteristic here of a very broad curve here between basically 3200, right, and 3500. Now look at this scale because it's different from the one we've seen on other IR spectra. This is, for example, only every 200. So we have to be aware of that. So get used to this. This is a characteristic swoop, if you will. Very strong, broad, strong because it's low here, and then broad because it's fairly wide compared to the others. So that's what you get with an ethanol. But let's go over here for a second. There's something else going on with an ethanol. There's that CO bond right here. Okay? Now, we're going to see that on the absorption table at 1000 to 1320, we should have something. The absorption table tells us if you have this, you should see something between 1000 and 1320. So there's 1000, and then there's 1320. Okay? So, which one is it? Is it this or this? At this point, it doesn't matter. You can look more specifically at that in college level work, but all we need to know is that there's something in here that supports the fact that we have an alcohol. So now we have two reasons to believe that there's an alcohol. This common swoop here, and then somebody in between 1000 and 1320. And again, these are telling us you have CH bonds. Now this is one of the more common peaks that we will see. All right, so now we have octanol. The difference here that we haven't seen yet is the presence of this C double bond O. That's called a carbonyl group. And that is here. That's going to be very characteristic. And you will see that that generally appears around 1760 to 1655. And generally we just call it 1760. So that double bonded group here shows up right here. Why is that important? Because this carbonyl group shows up in things like ketones, aldehydes, esters, and carboxylic acids. Also shows up in amides. So once you see this, at least you know you have 4 or 5 different possibilities. But the absence of this also tells you that you can rule out any of those things that we just talked about. And again, here's your characteristic CH bonds. This is just a more specific version, but a little bit different range. For example, if this is 2000 here, and this is 4000, right, then this is 3000, 2500. And so you just get a different shape because whoever produced this, whatever manufacturer, they just had a different scale here. But the general idea is true. This carboxylic acid has this big spread here between basically 3300 and 2500. So somewhere in here, 3300 and 2500. So that big thing there. But remember too that there's also this. So this is like peeking through. There's actually 2 peaks in here, and this one is kind of overlapping the other one. Okay. But here's another example. That C double bond O, that's right here. That's that C double bond O called the carbonyl group, not 1760 here, it's 1721. But look how nice this is, that it tells you also that you have the OH here, that you have a CO bond, and then another OH bond. Now, these are pretty specific. Okay, these are pretty specific, but they're helpful. Another version, now this is butanoic acid, but it uses a different scale, so it's not quite comparable, but you still have this business here. Now that CH bend you can see is poking through. If we could draw the separate lines, and this one would go like this, right? That CH stretch just to the right of 3000. Okay, this OH business is actually because of the acid, right? The carboxylic acid is this really big swoop, and they call it a jagged swoop here. But you see that's carboxylic acid. There's another characteristic carbonyl group, and this time it's this 15/16, just over 1700. Okay. There's some other things in here, but you'll see that this author did not really point them out like the last spectrum. Just another version of ethanol, and see, our absorption table doesn't quite tell us here. Our absorption table says there's something between 1000 and 1320, okay? But here they pointed out it's 1055 and 1102. But just, you see that OH group, take a look over here. And then this is very common. For a butanol stretch, right, if we have butanol here, we can lower this a little bit and see there's the structure for butanol. And I would point out that this hydroxyl group here, this OH coming off of carbon number 2, you see they're pointing out that you have a secondary carbon, right? Here's this carbon, and it's attached to two others, okay? At any rate, if this oxygen hydrogen group was over here, then you would get a different spectrum. It would be noticeably different, but not terribly different, okay? And then again, here's that alcohol group, and then somewhere in here is the CO bond that they're pointing out there. So why is this one useful? A couple of reasons. One, first of all, this is not a carboxylic acid, right? You need an OH group. Acids always end up on the end of the structure, so we don't really have that. But we do have a carbonyl group, and so that's easily found right here, that C double bond O. Saturated ester means there's lots of hydrogens, okay? Alkyl stretch we've seen before. But then there's just this that C single bond O, and we can see that here, 1055 to 1250. There may have been other peaks that were included in here that they just diminished, okay? That's why it's a little harder to read these over there. So just remember, though, that C double bond O tells us we have a variety of things. In this case, we know that it's ethyl acetate or ester. That also means ester. Now, if we look, the previous structure was ethyl acetate, but this one is ethyl benzoate. Okay, so there's still this C double bond O. So we see that over here. We see the C single bond O. They point that out. But here's something different. This is an aromatic, right? That's a benzene ring, and it's right here. Now, this is very small. Okay, that is a very small example. They're weak to strong. So in this case, it's not a very big thing. And maybe it's because it's being overshadowed by all of these other parts here. But we'll have you prepared for that. Let's not worry about alpha beta. This is a different version. And so now we have the amides. If you remember, an amide is a C double bond O, a carbonyl group with a nitrogen. Okay, so this is very much like the alcohols or carboxylic acid. Notice the transmittance reading here is different. Okay, so you have 0.2 instead of percent, they just use the decimals. And then there's a C double bond O. We don't have a picture of the structure though. Just one last look at a ketone. Very simple, but you'll see that all of those CH bonds here, that shows up in this region, and then your characteristic carbonyl group there, again at 1715. So a very simple molecule for what we're dealing with. And then if we wanted to, we could look a little bit closer at this guy, and that would be hexanone. And so it's not much different. It's still a very simple molecule here. And so maybe here we would see differences in the characteristics. just to recap then, this is a characteristic absorption table, and you can find any number of these on the internet or in your chemistry book, but there's a wide variety of them, and it depends on your professor as to what you'll use. Ours has reference letters that we included here along the side so that it's easier to find and make reference to in diagrams. These numbers are called the frequency values, but we can also call them wave numbers, because how many waves can you fit in 1 centimeter? And the only reason we do that is because it tells us in a value of numbers that's very readable, for example. So generally we'll talk about bond types, but what we're really saying is that these bonds, they stretch and they bend, and there's any other number of ways to respond to infrared rays. And then that tells us, though, if you have an OH group, you have an alcohol. And so we went through all of these to say that if we see a peak on a spectrum, come back to this table, and it might help you narrow down what you believe might be in the structure. And our final walkthrough, that this is called a spectrum. It's not really called a graph, it's called a spectrum. If you have more than one, it's called spectra. And so here we just talked about how the characteristic functional group, like this carboxylic acid, that entire thing is called a functional group. But this C double bond O is also a functional group. And you could even argue that the C single bond O is a functional group. It's really just a characteristic arrangement of atoms. Some of these over here, though, are a little too specific for what we do in high school organic chem. This is called the fingerprint region. It's very unique to this molecule. Okay? And then we saw some characteristic, very common structures. These peaks, for example, the carbonyl stretch or the carboxylic acid. So that wraps up our review of absorptions and spectra.